Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, it's a pleasure to have Grigory Yaroslavtsov here. So he graduated from Penn University, and he is an intern here at MSR. Today he will tell us about submodular functions.
All right, so welcome to today's talk. And so it's titled Learning and Testing Submodular Functions, and I will give an overview of this area together with some results that we had in Soda together with Sofia. All right, so let's get started. So the key property that we will study today is a property called submodularity. It's a property of functions. And you can think of submodularity as a discrete analog of convexity or concavity property, depending on the setting. So today, in today's talk, it will be mostly like concavity for functions on the Boolean hypercube. Or informally, submodularity is often described as the law of diminishing returns. So you will see why. And it has multiple applications in different areas, starting from combinatorial optimization and ranging to algorithmic game theory and other areas. So let me define what submodularity is. So we have a function over the domain, which is the Boolean hypercube. And we will also denote the domain as a collection of all subsets of some finite universe X. And this function takes real values, say, in the range from 0 to r. We have some upper bound on the values of the function. So the key notion here is the notion of discrete derivative, because I said that the similarity is like convexity or concavity is defined in terms of its derivative. So a discrete derivative of such function is defined as follows. So we think of the domain as being a collection of subsets of some universe, and we look at a certain element x in this universe, and we try to add it to a certain subset of element s where it is not yet present. Okay. So and we look at the marginal value, the marginal increase when we add this element to this subset, minus the value on the original subset. Right? So this is a discrete derivative on set S with respect to element x. And because submodularity is some analog of concavity, it requires that all these derivatives should be monotone. That the derivative on a bigger set t should be at most the derivative on a smaller set. So the derivatives should be monotone decreasing. Well, not strictly decreasing. Okay? So this means the law of diminishing returns. When you add an element to a bigger subset, your marginal increase is at most the marginal increase on a smaller subset. Right, so maybe let's stop here and make sure that this definition is clear. Yeah, please ask any questions, because it's crucial that you capture this definition. We'll work with it a lot. All right, so I will give some examples now. Right, so when you add this element, it should not be in the set. Huh? Otherwise, your value doesn't change at all. Hmm?
In the last inequality you said x not in T.
T is a super.
Right, T is a bigger set. So
if X is not in T,
it's not in T, it's not in S as well, right?
Oh, okay.
Right, so T is a bigger set, and derivatives are decreasing, non-strictly. Right? All right.
But it is trivially satisfied if it's on T, right? Inequality is trivially satisfied.
Right, yeah, sure. Right. That's why it is not in T, right? All right, and there are some examples that it will be useful to have in mind. So the first basic example is the coverage function. So suppose you have a collection of sets A1 to A and over a universe of size U, and your function is just, say, the total size of some collection of these sets. So suppose you pick a sub-collection of these sets S, and you evaluate the total size of their union. So it is easy to see that the coverage function is submodular, because when you have a strictly logical collection of sets, which is a superset of a collection, and you add a new set to it, then the marginal coverage increase can only be at most the marginal coverage increase when you add a set to a smaller collection, because some overlap could be already covered. So, and also it's important to know that the coverage function is monotone. So it will be crucial for us that submodular functions can be either monotone, like a coverage function, or they might not be necessarily monotone, like a cut function. So the cut function is associated with the graph. So suppose we have a graph here, and we define a function over all possible subsets of vertices of this graph. We pick a subset, like this green set on the picture, and we evaluate the total number of edges which cross from this green set to the rest of the graph, to the complement. And it's a more tricky exercise, but it's not hard to convince yourself that the cut function is also submodular. But you can see that it's not necessarily monotone, because when I have this green set being really, really big, my cut size can go down already. All right, so this distinction will be crucial. We have monotone and non-monotone submodular functions. And the type of questions that we will be asking today is, how can we approximate these functions? And the most basic version of this question can look as follows. Suppose I have a submodular function which have values from 0 to r, real values. And I have only polynomially many queries that I can ask to this function. So it has exponential size domain, but I only have polynomially many queries. So the question is, how many queries do I need in order to approximate this function? So this question was first studied by Gumans, Harvey, Iwata, and Mirokny, who showed that there is not much that you can do. So the best thing you can get with polynomially many queries is roughly square root of the size of the underlying universe approximation. This will be a multiplicative approximation in every point. And the construction that they give is shown on this picture on the right. So basically, the approximation that they give is pretty simple. You just take a square root of a linear function, which is shown on this surface, this red surface. And unfortunately, there will be these spikes. These are the true values of the function. And they deviate from this surface on some points. And that's why you get some pretty bad approximation. There will be these deviations from this approximating surface. So a natural question to ask next is, maybe we can relax the approximation guarantee. Maybe we don't really want to approximate the function everywhere, as in this work by Gumans. So here, note that we wanted to approximate for all arguments. So that's why we get this spike somewhere. And they really screw up the approximation. So maybe we only want to approximate the function on 1 minus epsilon fraction of points instead. And maybe this epsilon fraction will capture those spikes, and we will get a good approximation on the rest. So another way of formalizing this relaxed approximation guarantee actually corresponds to what is known as PAC-style learning with membership queries under uniform distribution. And it can be described as follows. So, OK. PAC-style learning is defined like this. So we want to construct a randomized algorithm A, which will approximate the function f. What does it mean? So the randomized algorithm A outputs a hypothesis, which is also denoted as A here. This hypothesis, suppose we want it to actually be exactly equal to f of s on 1 minus epsilon fraction of points. So this is this interior expression. So we have a uniformly random sample S from the domain. With probability 1 minus epsilon, the hypothesis A is exactly equal to the function value. And so this outer guarantee holds, suppose, over the randomness of A with some constant probability. OK, does this make sense? All right, so we just want to isolate this epsilon fraction of points, and we want to try to be exact everywhere else.
PAC is probably approximately correct. Probably correct.
Right. So probably correct means this 1/2. And approximately correct means 1 minus epsilon in the definition of PAC learning, right? So probably means that with some probability of the randomness of A, you will be approximately correct in the sense that you will be correct on 1 minus epsilon fraction of points.
There is a generalization called probably mostly approximate.
Right, that's the next slide. All right, so unfortunately, if you want to try to be exact everywhere, this is a bit too naive to hope that we can get much better results by isolating the epsilon fraction of points. And there is a result by Balkan and Harvey that shows that it's pretty much as hard as this original problem of trying to be exact everywhere. So we will use an approximate version of PAC learning. So the first approximation type that we consider is multiplicative approximation. So the setting is like this. So again, you have polynomially many in X queries. And you want to have a multiplicative approximation now on 1 minus epsilon fraction of points. So this is a model introduced by Balkan and Harvey. So we'll call this probably multiplicatively approximately correct learning. So the difference here is that we don't want an exact guarantee here inside, but we want an approximate guarantee with multiplicative factor of alpha. Okay?
Queries are also random?
So the queries are membership queries. You can query any point of your liking in this model.
So this also not like the PAC model where you get just random.
Right, so PAC learning, right, so I'm abusing a little bit the definition of PAC learning, but you consider PAC learning from random examples and from membership queries. Right, so here, for now I'm considering membership queries, but definitely there are some results on random examples as well, but I'm just not stating them here to simplify the presentation a little bit. All right, so in this multiplicative model, what Balkan and Harvey showed that you can get slightly better approximation. So actually, the previous root 10 approximation has some log factors in it as well. So they get just square root of x approximation, the square root of the size of x approximation. But not much better is known in PMAC model. And related version of approximation is additive approximation, where you don't want to have a multiplicative, but rather an additive approximation here. So in this interior expression, you have a beta parameter which bounds the additive approximation in every point. So this actually has some motivation in privacy. This is why it was studied intensively. And there are different results here by Gupta, Hart, Roth, and Ullman, and by Shirachi, Clemens, Katari, and Lee. So what I want to show here is that the dependence on the precision here is exponential. So what you get in terms of beta is like the size of x to the power 1 over beta squared running time and query complexity. So R is the upper bound on the maximum value. So we have a range from 0 to R. Okay. And I will just put all these together on a single slide so that you can look at them closely. All right, so there is this. Yeah, so in this slide, I actually fixed epsilon to be a constant to simplify what's going on. So we have this pioneering Gumans-Harvey, Vatami-Rockney multiplicative square root of the size of x approximation. We have this Balkan-Harvey paper, which gives PMAC learning algorithm. We have these two additive learning algorithms. And today I'm going to show a new result that we have with Sofia Rashodnikova, where we show actually a PAC learning algorithm. So now that if you have an arbitrary submodular function which takes real values like this, it doesn't really make much sense to ask for an exact learning algorithm, because the function is real valued. So what does it even mean to try to be exact with respect to this function? Clearly, you cannot do much. I mean, because function can take average real values, and you have to output them exactly. So that's why basically there is nothing for PAC model on this slide, except for this work where we consider discrete range. So suppose that the function takes discrete values from 0 to r. So now it makes sense to ask to be exactly correct on the values of this function. And we actually show that you can get much better learning algorithms for this case. So an actual correspondence with the previous work would be to try to fix, say, the additive error to be roughly 1 over, to be basically a constant, like say 1/3. And so once you have an additive error 1/3, you can also get exact values of function which takes values from 0 to r, right? Because you can just run your additive error algorithm and just round all the values to the integral values from 0 to r. So this is an actual starting point. But unfortunately, this previous additive learning algorithm would give you exponential dependence, like size of x to the power r squared. So we actually show that with respect to the number of values that the function takes, PAC learning only requires the dependence which is polynomial in x, some fixed polynomial, and some function of r, which corresponds to some kind of fixed parameter tractability with respect to the number of values.
So why can't you convert your algorithm to an additive?
Oh, so basically the short answer is like this. So so it only works in one direction. Once you have an additive, you can get this. But in the other direction, if you want to discretize the value of a function, then our algorithm crucially relies on the fact that the function is submodular. But if you discretize a submodular function, what you get is not necessarily a submodular function anymore. Does it make sense? I mean, like you start with a submodular function, which takes, say, real values from 0 to r, and you round them to integers from 0 to r. And, well, there are examples when it's no longer submodular after you do this. And our algorithms rely on this. So, but in the other direction, it is true. If you have a learning algorithm for with additive error, then you can run this algorithm and then round the values.
Does it just break locally, or can it cascade and break really?
It seems to be breaking pretty badly if you try to, to do this. Yeah. So there was a question. Oh, a similar question. Okay, great. Yeah, that's a good question to ask. All right. So.
When you say time, like time over here is always queries, right?
Not actually. So here is the actual running time. So so the number of queries for for all algorithms except for the last one is actually pretty much as the running time, and for our algorithms it's actually less queries. So it's not polynomial in x, but it's rather polylogarithmic times this function of r. So this would be the query complexity of this PAC learning algorithm.
The main dependence here is on R.
Yeah, basically, yeah, right. So for the query complexity, yeah, the main dependence is on R. And all right, so just to make sure that I don't oversimplify things, so this is all stated for uniform distribution, and this is all stated for learning with queries. And some of the previous work, it actually has stronger guarantees. For example, the Balkan and Harvey upper bound works under arbitrary distribution, and some of these additive learning algorithms, they also have some nice properties. They may allow some tolerant queries and some different kind of queries, and they work. So, for example, the Chirachi works in agnostic setting, if you know what that means. All right. So I will explain how to get this PAC learning algorithm, which I introduced here in the last column. And it relies on the following structural result that we show, is that every submodular function, which takes integer values from 0 to r, can be represented by a formula which has width big O of r. So it's not going to be important that the function takes these values from 0 to r. It can be any values as long as we have at most r plus 1 many of them. We still get a representation by the small width formula. And from that, pretty much, you will be able to derive those learning algorithms. I will tell later how to do this. All right, so let's continue. All right, yeah, maybe like this is a statement of results. Maybe it's another good place to ask questions if you have any.
Any lower bounds known except for the one you mentioned first?
Yeah, there are lower bounds. So for example, one lower bound says, so it's a more recent result, which is not mentioned here. It says that in any pretty much learning model, you need exponential in R many queries complexity.
And it's applicable to your model as well?
Yeah.
Nina's paper has an x to the 1/3 approximation lower bound for polynomially many queries.
Right. Right. Yeah.
What's the model here? Is it an arithmetic formula or what's the model for a formula here?
So model for the formula. So you can think of it pretty much as a KDNF, R-DNF, order R-DNF. So the only difference is going to be that because a function takes integer values, it won't be a Boolean formula, but it will be some generalization of R-DNF to non-Boolean values. I will tell later. We'll get to this. But yeah, to get some intuition, that's what it is. So that will be just a maximum number of literals in every clause. And a clause is like a Boolean clause in a way, pretty much.
In PAC, you exactly says that what's the value of f, right?
Right, yeah.
So you mean that, for example, if R is constant, you only need polylog queries to figure out all the values exactly?
Yes.
So even for example, for okay. Just figure.
Yeah, but there is some dependence on epsilon, which I'm actually hiding here. So the dependence on epsilon is going to be like R to the power exponential in 1 over epsilon.
What is epsilon here?
Epsilon is a fraction of points where you can be incorrect.
Oh.
Make sense?
Yeah.
All right, good. All right, so yeah, all right. All right, since all this previous work and our work happened, there have been subsequent progress, which I want to mention only briefly and just explain, like tell you roughly what the techniques are used. So in our work, we use approximation by pretty much like R-DNF looking formulas. So in subsequent work by Feldman, Warnock, and Kothari, which appeared very recently in Call 2013, they use approximation by decision trees instead. Further subsequent work uses approximation by juntas to get good learning algorithms. So roughly what happens here is once you have an approximation by R-DNF, it's not that hard to show that you can approximate by decision trees and juntas. But if you actually use these more refined techniques, then you get better parameters. So specifically for the setting that I considered, on the previous slide for this PAC learning of functions with values from 0 to R, you can get better results in terms of dependence on R and epsilon. And so the flavor of the results is you try to minimize the number of variables that your approximation depends upon. And for example, the work of Feldman, Warnock, and Kothari, the first subsequent work, it shows that submodular functions can be approximated in L1 and L2 distance by juntas, by functions which depend on exponentially many variables, 2 to the power R or epsilon to the power 4th, which is not very surprising, actually, given the previous results. But what is actually very surprising is that you can actually approximate them by juntas which have only polynomially many variables. OK, so I want to actually mention this only briefly. If you're interested in this, let me know, and I can give you the references. And, I will be happy to talk more about this, but let's maybe continue. So before we jump into the technical details, the final introductory slide that I want to show is that submodular functions actually live in a bigger family of all kinds of functions which are interesting for algorithmic game theory and other applications in mechanism design. So submodular functions are actually part of this hierarchy, which is shown here. So this hierarchy comes from the Nissan, Lehman, and Lehman paper. And so submodular functions are a subclass of fractionally subadditive functions, which are in turn a subclass of subadditive functions. So all the results which are known for the superclasses of subadditive functions also apply to submodular functions. And there are some subclasses of submodular functions which are of specific interest, like coverage functions we have seen on the second slide. And there are some other classes. So there is a number of results for specific classes, which I'm not going to mention in more detail, but they are summarized here on the right. So specifically, coverage functions have attracted lots of attention, and some restrictions of submodular functions. All right, so now we go to the technical details. So I'm going to describe how to represent submodular functions with discrete range by formulas. And before we start, I will try to give you some basic intuition why it is possible to represent them by such formulas. So the main intuition here is that submodular functions with discrete values can be captured by their values on the boundary. So how does it work? So as I said, for the purposes of this talk, submodularity is similar to concavity. So let's look at concave functions, which are defined on the real line, well, discretized to points from 1 to n, and which take only discrete values from 0 to r, where r is less than n. So, and as I said, submodular functions can be monotone, and for the purposes of this talk, it will be much simpler to look at monotone functions first. And all the results pretty much are going to generalize to general submodular functions. So the most basic example is the monotone concave function. So suppose I have a monotone concave function which takes r plus many values. So how does it look like? So as I said, the key intuition is that it's captured by its boundary, which is indeed the case for monotone concave functions. So if a function only takes r plus many values and is a monotone concave, then it actually becomes a constant after it reaches its maximum value, which happens at point the domain reaches at most r. And after that, this function cannot grow anymore because it is concave. If it was to grow here somewhere, then it would violate concavity. And it only takes at most r plus 1 many values, so it has to reach its maximum within the first at most r many points. Does that make sense?
Why can't it stay flat for some time?
So if it stays flat, then it stays flat. It cannot grow again, right? So if it starts to grow somewhere here, it will violate concavity, right? Because like I will pick this flat region together with this point, which grows, and that will be convex instead of being concave. So it has to be curved downwards, cannot curve upwards. All right, so that's the basic intuition why monotone concave functions are fully described by their boundary, which consists of at most r many points on the left boundary of the domain. All right, so and general concave functions turn out to be only twice more complex, so they actually have two boundaries, one on the left and one on the right, and in the middle they have to be constant. So you can convince yourself that this is true. So this is the first source of intuition. So the second source of intuition is to look at the hypercube domain. So suppose we have a function on the hypercube now, and it takes discrete values from 0 to r. And suppose we actually consider the most basic case when r is equal to 1. So when the function is just Boolean submodular function. So let's do this case study. R equal to 1, have Boolean submodular functions. And it is actually known that monotone submodular functions are exactly monomials, namely disjunctions of Boolean variables. So this is a one-to-one correspondence. Every monomial is a submodular function, Boolean submodular function, and vice versa. And general submodular functions with Boolean range can be described as a two-term CNF. They can be described as a conjunction of two disjunctions. One of them is strictly monotone, only has positive literals, and another is strictly negative, only has negative literals.
So what does this mean? So the monotone, so that's a Boolean function, right? How do you get? Oh, this is cosine.
Makes sense? All right. And this is also a one-to-one correspondence. So if you are a Boolean submodular function, then you can be represented by this two-term CNF, and vice versa. All right, so and the general proof of the structural result combines these two intuitions, the intuition from the line and this intuition from considering Boolean functions. So consider the hypercube domain, which I shown this picture. So the hypercube here is pictured as follows. So we order all sets in the domain. So we have like the universe X, and we have all possible subsets of X ordered by their size. So we have an empty set on the bottom, and the subsets are ordered by their size in layers. So what I'm going to show is that monotone submodular functions with R many values are fully captured by their boundary, which in this case corresponds to the region consisting of sets of size at most R. And general submodular functions will be captured by their two boundaries, one corresponding to sets of size at most R, and another corresponding to sets of size at least size of X minus R. All right, so let's see a proof. So I'm going to show the proof for monotone submodular functions and then give some ideas how to generalize it to general submodular functions. So for monotone submodular functions, it's actually quite simple.
Sorry, can you go back to what do you claim for the general submodular function?
For general submodular functions, basically the idea is that once you know the values of the function on sets of size at most R and on sets of size at least the size of X minus R, you can fully determine the values here in between on all other points. Okay? All right, so monotone submodular functions. So consider again the hypercube on this picture. So this is a hypercube ordered by the size of the set from bottom to top. So here on the bottom is the empty set, here is the universe. And consider the collection of sets of size at most R. This is this bottom region on the picture. So the first idea is because our function is monotone, if I take some set here on the bottom, say set S1, and the value of the function is f of S1 here, then everywhere above, on all supersets of this set, the value of the function is at least f of S1, just by monotonicity of the function. Now if I take another set S2, here on the bottom, and I consider the region of points above S2, the value is at least f of S2. So if I intersect these two regions, then the value will be at least the max of f of S1 and f of S2 in the intersection of these two regions. So the naive approach, given this observation, is to write the following formula. For every point t in the domain, I can try to express f of t as a maximum over all subsets S of t of size at most R of f of S. And it turns out that this is actually an exact expression. So the theorem says that for monotone submodular functions, this will give you exact value of f of t. All right, so consider some point t in the domain. And this region corresponds to all possible subsets of t. And we take the maximum overall sets as subsets of T, which are in the intersection of these two regions. Right? So we take the maximum overall as subsets of T, which have size at most R. Does that make sense? All right. So as I have just shown, just by monotonicity of the original function, we didn't use anything else, f of t is going to be at least the maximum, taken over this subset of size at most R. So the key part of the proof is the opposite direction, to show that f of t is actually at most its value. All right, now consider, again, this point t somewhere here in the hypercube. And then consider a set S prime, which is the smallest subset of t, which has the same function value. Namely, f of S prime is equal to f of t. And it is the smallest one. You cannot remove any element from S prime without violating the property that the value is the same. So because this is the smallest such set, for every element x in S prime, if I try to remove an element from S prime, this element x, then the value of the function has to go down, which means that on every element which is in S prime, the derivative on S prime minus x on the element x is strictly positive. This is just by the choice of S prime. So if my set S prime is here, then on any element which I can remove from S prime, on any element present in it, the derivative is strictly positive. And recall that the function is submodular, which means that its derivative is monotone decreasing. So if the derivative is actually strictly positive here, then it's strictly positive on all subsets of S prime on those elements which are in S prime. Okay? Which means in this green region, which corresponds to all subsets of S prime, all the derivatives on the elements of S prime are strictly greater than 0. So because the function takes at most r many different values, it means that on every path, the value of the function strictly increases in every step. And it means that the set S prime can only have size at most r, because the function has to decrease every time, and it can only increase at most r many times. This is roughly the same argument that I used on the line to show that the value of the function is fully determined by the first r many points. All right, so this means that the set S prime is actually fully contained within this region. It has size at most r. And that means that the value of the function at point t is at most this max, because there is some point which actually makes its value exactly f of t, and it's a point corresponding to a set of size at most r. Okay? Makes sense? It's probably the most technical point so far. So
this should also follow from the fact that all matroids can be characterized by all its independent sets, right, in some sense.
but maybe then you need the function to be a rank of a matroid, or?
But more or less, monotone summary functions are rank functions of matroids.
Oh, really? You're saying that any monotone summary function is a rank of some matroid?
Yeah, like if it is a ground set, but more or less that is true. Yeah, but because at least let's say 0, like consequent of the 0, 1 value, basically then your theorem exactly this set that you said would be exactly the largest independent set you make, right?
Mm-hmm. I see.
If it's not, you have to be a bit careful. If it's not, like consequent is not 0 value, then you have to be a bit careful how you define it, but more or less it should follow from.
I see, that's interesting. I see. I see, yeah, I'll be happy to discuss that. All right, so we have just seen that we can represent a monotone submodular function using this expression which takes the maximum overall set of size at most r of f of s. And to jump to the learning theoretic results, I will need to switch the notation a little bit to go from this set theoretic notation to more functional notation. So we'll replace the size of the universe by n, and we will replace the collection of all subsets by the indicator variables x1 to xn, which are Boolean variables, which indicate whether a certain element is present in the set x, sorry. So, and let's recall what a Boolean KDNF expression is. So a Boolean KDNF is a formula which is a disjunction of a collection of clauses, each having at most k literals, and every literal is either a variable or negation, and you take a conjunction of this literals to get a clause. So because our functions are not Boolean, we'll use what we call a pseudo-Boolean KDNF. So instead of disjunction, here we'll use a maximum, and every clause will have a certain constant a sub I associated with that, and the value of a sub I is just some value from the range of the function. So in the Boolean case, well, basically max is just the disjunction, and all the constants will be 1. So the pseudo-Boolean KDNF expression is a maximum over a collection of Boolean expressions of width at most k, each multiplied by a certain constant. And we say that such a formula is monotone if it doesn't have any negations in any of its terms. So in this language, the previous theorem can be equivalently restated as follows: that every monotone submodular function f can be represented by a monotone pseudo-Boolean R-DNF, where constants are taken from the range. So now that it's just a coincidence that it so happens that both the width of the formula and the constants are both bounded by R. In general, these can be different. But so here it so happens that the values are from 0 to R, and the width by this result is also bounded exactly by R. So in general, it doesn't have to be the case. Okay. So for general submodular functions, I will just state the result and give some intuition for how to prove it. So if you have a general submodular function which takes values from 0 to R, then you have to increase your width by a factor of 2. So it will be a 2 R-DNF expression. It will no longer be monotone, but it still will have constants from the range from 0 to R. So the hint, which is the crucial observation in the proof, relies on the following construction due to Lovász, which we call submodular monotonization. So the idea is to reduce the general case to the monotone case somehow, and this construction allows us to do this. Given a submodular function f, you can define what we call a monotonization of the submodular function f monotone on every point s as follows. If you take the minimum over all s, overall supersets of s of the function value f of t, and make this f monotone of s, then it's easy to see that it will be a monotone function. Well, because for a smaller point, you take this mean over a larger collection of sets, so it will be monotone. So the tricky part is to show that it's submodular, but it's also not too hard. Okay. So, and I will skip the details of the proof for now. So the idea is to do some reduction to the monotone case. All right. So in the rest of the talk, I'm going to show how to derive some consequences of the structural result for learning and testing properties of submodular functions. So the key idea is that basically you can reduce learning these pseudo-Boolean formulas to learning KDNF formulas in a pretty simple way. So let's denote the class of pseudo-Boolean formulas which have width k and constants taken from the range from 0 to r as DNF kr. So here I use different parameters. So in our proofs, k was either r for monotone functions or 2r for general submodular functions. But I will use the different parameters here, k and r. So the reduction is actually pretty basic. So the idea is to just define the corresponding Boolean indicator functions which we're going to learn. So we call them I slices of the original function. So suppose you have a function which takes values from 0 to r. You can define these Boolean I slices, which are Boolean functions, as follows. So f sub I is equal to 1 if and only if the value of the function f exceeds this threshold I. And we can reduce the problem of learning the pseudo-Boolean formulas with constant from 0 to r to learning these I slices of these formulas. So you can represent a function which takes r values as a maximum over its I slices. You just multiply them by their thresholds and take the maximum over all of them. So and just remind that we want to do PAC learning, meaning that we want to be exact on 1 minus epsilon fraction of points with probability 1/2. So this can be done as follows. We can learn every I slice of the function f on, say, 1 minus epsilon over r fraction of arguments. And then by union bound, if we have all those I slices correct on that many arguments, then we only make mistakes on 1 minus epsilon fraction of arguments overall if we take the max over all those I slices that we learn. So this is a strategy, learn f sub I, which is a KDNF formula now. Yeah, so this is a key observation maybe that I skipped. Well, once you have a pseudo-Boolean DNF kr formula, and you take an I slice, then you actually get a KDNF. That's the key observation. Right, so, and those KDNFs we know how to learn pretty well. So what I want to describe the technical ideas of what is involved in KDNF learning. So if you want to learn a KDNF with membership queries, then the key property that allows for efficient algorithms is the fact that KDNFs are actually very well concentrated on a certain number of Fourier coefficients, which is pretty small. So let's define what is called Fourier sparsity of a class of functions. This is the number of Fourier coefficients that you need to recover, the largest Fourier coefficients that you need to recover, in order to have a PAC learning algorithm for every function with precision epsilon. And it turns out that for KDNF, this number of Fourier coefficients that you need to recover only depends on the width of the KDNF. It doesn't depend on the number of variables at all. So this is a very nice result by Mansour, that in order to approximate the submodular function on 1 minus epsilon fraction of points, you only need to query a certain function, k to the power big O of k log 1 over epsilon, many highest Fourier coefficients of this function. No dependence on the number of variables. Again, I want to stress this. So, and once you know this, you can leverage your favorite algorithm for learning Fourier coefficients. There are different algorithms, like, for example, Cauchy-Levin's Mansour algorithm or Goldreich-Levin, which does this in time-ambitious polynomial in n and this sparsity parameter, s sub f. Or you can use maybe some more recent algorithms which do what is called attribute-efficient learning, which allows to reduce the number of queries from polynomially many in n to polylogarithmic in n, and still you have some polynomial dependence on this sparsity parameter. And this is basically what we can use together with the structural result that I have shown in order to get those learning theory results that have been shown in the table, right? Because we basically get this polylog n many queries times some polynomial of this s sub f, and in our case s sub f is well, so you put k equal to r, you get r to the power r log 1 over epsilon, and this is the number of queries that we get. All right, so there are some weak lower bounds. All right, so Yeah, so this is basically the sparsity of DNF kr. It's going to be k to the power k log r over epsilon. There are some minor optimizations that you can do on top of this, but that's the main idea. And another application that I want to show is to the area of property testing. So again, let's see be the class of submodular functions which take R values. Now I want to solve a somewhat simpler problem. Instead of trying to approximate the function everywhere, or on one exceptional fraction of points, I want to ask the following question. Given an access to a function, can we test whether the function is actually from this class? Just output a single bit whether the function is in the class or not in the class. And the decision is going to be made approximately in some sense. And I will explain in a second how. So a property testing algorithm is a randomized algorithm for distinguishing two situations. Situation number one is a function f is in the class, in this case, say, submodular with r many values. So this is the class of functions that we're interested in. So this is the first option. F is in this class. And the second option is that f is epsilon far, namely differs on at least epsilon times the size of the domain, epsilon fraction of points of the domain points from any function in C. So this is the epsilon far case. And there are some functions which are epsilon close. So those are the functions for which you can output any answer. All right, so the key idea for property testing algorithms is that KDNFs actually have small representations not just in the Fourier domain as for the learning. So in the learning, we saw that KDNFs can be approximated by a number of Fourier coefficients, which is just some function of k and epsilon. It turns out that actually KDNFs have small representations by formulas. Namely, there are some KDNF formulas which have small number of variables which can approximate them pretty well. So there is a fairly recent result by Gopal and Mack and Ringgold, which shows that for every epsilon and for every KDNF formula, you can efficiently sparsify this KDNF formula. So your original KDNF formula, it can potentially have, say, n to the power of k many different clauses, right? Because you can have all possible subsets of variables, and you can also have negations. So this result by Gopal, Mack, and Ringgold, it shows that actually you don't need n to the k many clauses. You can do with the number of clauses, which is only a function of k and epsilon again. Again, no dependence on epsilon. Oh, so sorry, no dependence on n. And this KDNF formula will be approximation to the original formula on 1 minus epsilon fraction of points. So effectively how the algorithm works is starts with this big DNF formula that you have. And it shows that there is a certain subset of its clauses, where the number of clauses is only a function of k and epsilon, which actually gives a good approximation. So, and this is actually what we can leverage for property testing algorithms, using the following approach, which is called testing by implicit learning. So now that on the previous slide, what we have seen is that our KDNF formulas can be approximated by formulas which only depend on small number of variables. Because every clause has at most k variables, once you have a small number of clauses, you also have a small number of variables overall. So KDNF formulas can be approximated by juntas, functions which only depend on j of epsilon many variables, and the number of variables is k log 1 or epsilon to the power big O of k. And this is the crucial property which allows to design property testing algorithms. Once you have an approximation by small juntas, you have efficiently property testing algorithms, pretty much. So we can test whether the function is submodular with r many values with query complexity, which is only a function of r and epsilon, which doesn't depend on the number of variables at all. And in subsequent work with Blay, Onyx, and Servideo, we show that actually we can show a more precise characterization, which is exact for submodular functions with r many values. And this gives a better dependence on the number of variables in this Hünter approximation. And I just want to mention some previous work on testing submodularity. So submodularity for real valued functions seems to be a very tricky property to test. The best upper bound that we know is 1 over epsilon to the power big O through 10. This is from the work by Seshadri and Vondrak. And the only lower bound is linear in n. So there is still this big exponential gap. There are some results for special cases. So the gap is, yeah, pretty big. And to conclude, I want to show some other directions which seem to be interesting. So in this line of work on learning submodular functions, there is a number of results on approximating these functions by all kinds of representations, by Hünters, decision trees, formulas. One question is whether we can leverage these results for optimization of submodular functions. This seems to be challenging because if you want to optimize a submodular function, it's actually crucial to know its values everywhere as compared to 1 minus epsilon fraction of points, because maybe the optimum value is exactly on that epsilon fraction and you don't know it. But maybe these structural results actually still tell us something interesting. Question number 1. And question number 2 is actually, because we have some approximation results with respect to distances other than Hamming distance for L1 and L2 distance, it will be interesting to study testing whether the function is close to submodular with respect to L1 and L2 distance. So this might help overcome this big exponential gap on the previous slide, which is known for Hamming distance. So, and actually there are some results by Feldman and Vondrak, still unpublished, and published results by Baron Rasodnikova and myself, which have some progress in that direction. All right, thanks. So that's pretty much it.